Hello and welcome to today's video in which we're going to be looking at a second example on circular measure. We're going to be looking at question 6. Again, this is a Cambridge A-Level past paper, May-June 2018, paper 12. The diagram shows points A and B on a circle with center O and radius R. Like I said to you before, whenever you're answering a problem in these questions, you always want to read each statement and interpret or analyze what that statement is saying. So if we analyze the statement, this statement has told us that the center of the circle is O and the radius is R. So if we analyze the statement, if the radius is R, then we can also see that OA is equal to R, because OA is also the radius of the circle, because we're going from the center of the circle to the circumference of the circle. So this is R, and this is a sector therefore. The tangents to the circle at A and B meet at T. Let's analyze that a bit more. Circle theorems. You did this in GCSE maths. One of the circle theorems that you learned is when you have a point, for example T, and then you have two tangents coming from that point, in this case BT and AT, and they are going to touch the circumference of the circle, in this case A and B, then the length of those tangents are equal. The lengths of those tangents are equal. This is from your GCSE math circle theorems. And another concept that you learned in circle theorems as well is that when you do have that tangent touching the circumference of the circle, if you draw a straight line, a vertical line from the center of the circle to that tangent, the angle is 90 degrees. So we know that this angle is 90 degrees and we know that this angle is 90 degrees. So this statement here alone has told us two things. The tangents to the circle at A and B meet at T. That statement has told us two things. It has, one, told us that these two angles are 90 degrees, and two, it has told us that BT is equal to AT. The shaded region is bounded by the minor arc AB, this is the arc here, AB, and the lines AT and BT. Angle AOB is 2 theta radians. In the case where the area of the sector AOB, the area of this sector, is the same as the area of the shaded region, show that tan theta is equal to 2 theta. So whenever you're doing a show that question, literally interpret what you've been told. What you've been told is that the area of this sector is equal to the area of the shaded region. So, what is the area of the shaded region? Well, the area of the shaded region, well, this is a kite, by the way. Okay, this is a kite. Yes, how do we know that this is a kite? Now, remember that we deduced that BT is equal to AT, and we also deduced that this is R. This is R. So, OA is equal to OB, and BT is equal to AT. What does that tell you? It tells you that this is a kite. Remember that a kite looks like this, but for you to know that it's truly a kite, these two sides must be equal, and these two sides must be equal. And we know that BT is equal to AT, and we know that OA is equal to OB, so this is definitely a kite. And remember, the way we deduced that BT is equal to AT, we used circle theorems to say that we have a point here, two tangents touching the circle from the same point, so those two lines are equal. You did this in GCSE maths. You can research on circle theorems if you've forgotten about those, but those are very important. And OA is equal to OB because both of them are the radii of the circle. So this is definitely a kite because this is equal to that and this is equal to that. So how do we find the area of the shaded region? Well, the area of the shaded region is the area of the kite minus the area of the sector. That's the area of the shaded region. Okay, so the area of the shaded region is equal to the area of the kite minus the area of the sector. But the question has told us that that area is equal. It has told us that the area of the shaded region is equal to the area of the sector. If the area of the shaded region is equal to the area of the sector, we're then going to interpret that here and say that therefore that area of kite minus area of sector, it's equal to the area of the sector. Okay? Now I'm just going to abbreviate this to K and I'm going to abbreviate this to S. Okay? So instead of kite I'm just going to write K, and instead of sector I'm just going to write S. Now these two are like terms. You can take this because the area of the sector is just the area of the sector. You're going to take this that side. So the area of the kite is going to be twice the area of the sector. So the entire area of the kite is going to be the area of the sector doubled. So if you take the area of the sector and you double that, you're going to get the area of the entire kite. Now, how is this going to help us show what we need to show? Well, bear with me. Let's go on. So now we want to figure out what is the area of the kite. What is the area of the kite? Well, what do we do? What do we do? You always want to create a triangle somehow. We can create a triangle, and in this case I'm going to use a different color. I think I'm going to use the color red because red seems like a nice color. I'm going to use the color red, and what I'm going to do is I'm going to come from the center here and I'm going to come over here. Split this into two. Okay, good. Okay, so what have I done? I have split this kite into two. I've split this kite into a half. Okay, so if this entire angle was 2 theta, then I know that this individual angle is theta, and I know that this individual angle is theta as well. Because this thing, it's in a half, theta plus theta will give me the big angle, which is 2 theta, which I have here, 2 theta radians. Now, if I split this into 2, what does this do? If I split this into 2, what does this do? I form 2 triangles. This is one triangle and this is another triangle. But from my circle theorems, I know that if this is a tangent, then I know that this is 90 degrees, like I deduced before. That's 90 degrees. From our circle theorems, we can deduce that this is 90 degrees because, you know, like we said before, it's 90 degrees. So this is a right angle triangle. This is a right angle triangle. This is another right angle triangle. So if I find the area of these 2 triangles and add them together, then I'm going to find the total area of the kite. Because what I've simply done is I've taken the kite and I've split it into 2 different triangles. So I know that since these 2 triangles are exactly the same, if I find the area of this individual triangle, then that is equal to the area of this triangle. If I add the 2, I get the area of the entire kite. In other words, the area of the entire kite is going to be twice the area of this right-angled triangle. Let me go back to gold and let me write that down. Okay, T stands for triangle in my analysis here. So the area of this kite here, which is equal to twice the area of the sector, is equal to twice the area of the individual right-angled triangles. Now, how do I find the area of a right-angled triangle? Well, it's going to be a half base times height. It's going to be a half base times height. Half multiplied by AT multiplied by R. AT is the base of the triangle and R is the height of the triangle. But how do I find AT? How do I find AT? Well, if this is a right-angled triangle, I can simply use SOHCAHTOA. I can simply use SOHCAHTOA. Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tan is equal to opposite over adjacent. So I'm going to look at my angle theta here, and I'm going to say that the tangent of that theta is equal to the opposite over the adjacent, which is r. So the tangent of theta is equal to AT over r. Because remember, I deduced that BT is equal to AT, so AT is equal to R times tan theta. This is just simple trigonometry from your GCSE, so that is what happens. So the area of the triangle, therefore, is equal to a half multiplied by R tan theta multiplied by R. And what does that give me? So this is the area of the triangle, which is a half r squared tan theta. So the area of the kite is going to be 2 times a half r squared tan theta, which is just going to be r squared tan theta. So this is the area of the kite. So the area of the kite is going to be r squared tan theta. Remember, I said the area of the kite is twice the area of each triangle. If this is the area of each triangle, the area of the kite is twice that, so it's r squared tan theta. How does that help me? I go back to this interpretation here. I go back to this interpretation here. Now I need to find the area of the sector. I now have the area of the kite. Now I need to find the area of the sector. Now I know that the area of a sector is given by a half r squared multiplied by theta, where theta is the angle. But theta in this case is 2 theta because the angle is 2 theta. As you saw here, the angle is 2 theta. We're looking at this sector. The angle is 2 theta. So I know that the area of my sector is going to be a half r squared multiplied by 2 theta, which is just going to be r squared theta. So this is going to be the area of my sector. 2 half times 2 is just 1, so r squared theta. So now I can plug this in here and say the area of the kite is equal to twice the area of the sector. And then what do? I divide both sides by r squared. If I divide both sides by r squared, I'm going to have tan theta is equal to 2 theta. And that's what the question has asked me to show. The question was, show that tan theta is equal to 2 theta. And that's exactly what I've done here. In the next video, we're going to look at part 2. So if you enjoyed the video, if you found the video useful, please comment on the video, like the video, subscribe to my channel, share the news about the channel, and until next time, take care. And what about the media?